In previous sections, we've seen matrices. We've seen coefficient matrices. We've seen augmented matrices. We've used elementary row operations to transform them into row echelon form or reduced row echelon form matrices to be able to solve systems of equations. But starting in this section, we want to formalize the ideas of matrices and what we can do with them. So a matrix is a rectangular array of numbers. So for example, matrix M might be 1, 3, 4, 2, 0, -1, 0, 5, 4, 9, -3, 8. Okay, so matrix M is a matrix. It is a rectangular array of numbers. It has rows, it has columns. By the way, the plural of matrix is matrices. Okay? Now, we can talk about the size of a matrix based on its dimensions. The dimension of a matrix is defined as m by n, where m is the number of rows and n is the number of columns. So notice which number goes where matters here. The rows always go first, so rows by columns. Okay, so in our example here, M is a 3 by 4 matrix, okay, because it has 3 rows and it has 4 columns. Okay, we sometimes summarize this by writing M has real number entries and 3 rows by 4 columns. Okay. Now, we already have a lot of experience with matrices, not just our augmented matrices and our coefficient matrices, but all the vectors we've looked at are special cases of matrices. An n-dimensional column vector is an n by 1 matrix. Okay, it's a special kind of matrix. When we write that vector as a column vector with n numbers, it has n rows and 1 column. Okay. An n-dimensional row vector is a 1 by n matrix. So by a row vector, I mean we are writing it horizontally, so there are n numbers written in a single row. So it has 1 row, and the n numbers are each in their own column, so n columns. Okay, let me give you a concrete example to see. Okay, so if I have, let's do a column vector first, actually. Most of the time we use column vectors. So if I have 3, 1, -2, that is a 3 by 1 column vector. 3 rows, 1 column. On the other hand, 2, 5, negative 3, 1 is a 4 by 1, I'm sorry, 1 by 4 row vector. It has just one row and 4 columns. Okay, so a vector in this sense is a matrix where either it has only one row or only one column. We reference the individual entries of a matrix by which row and column they're in. Okay, so for example, if I have a matrix A, I might write it this way. And this says, hey, I'm focused on the individual entries of the matrix A in the ith row and the jth column. So if I write that out a little more formally, I'd have A11, A12, all the way to however many rows I have, A1n. Next row, A21, A22, all the way to A2n. So notice what's happening here. The subscript here, the first number in the subscript, reference the row number. The second number in the subscript references the column number. So A12 is the entry in the first row and the second column. Okay? So you go all the way down to your last row, the mth row. So AM1, AM2, AMN. Okay? So if I want to write out all the entries, the subscripts tell me which entry goes where. Okay? I could also use this notation if I don't want to spend time writing all of this out. This just tells me, hey, I want to talk about the individual entries of matrix A, and when I give the subscripts, those just references the row and column. Okay? So generally, we reference the entry of a matrix by its row and column. For example, if matrix A has entries A sub ij, then A35 is the entry in the third row and fifth column of matrix A. Okay. Now, we only add subscripts when we are talking about the entries as variables. If we have concrete entries, for example, this entry right here, that 9, we wouldn't say 9 sub what? 3, 2, right? Because it's in the third row and second column. We wouldn't do that because we don't do that if we have a number as our entry. Instead, we'd write it out. 9 is the 3, 2 entry of matrix M. Okay, third row, second column. And sometimes when we have a matrix, it's going to be useful to focus on the individual rows or the individual columns of the matrix, to think about them as vectors. Okay, so if we want to do that, we could imagine the individual rows and columns of a matrix as vectors. We can also think about the rows of a matrix or the columns of a matrix as vectors. So we might say something like A is equal to the matrix where the columns are vectors C1, C2, all the way to Cn. Okay, and then to emphasize that they're vectors, sometimes we just leave it like this. But sometimes to emphasize that we're vectors and it takes up the whole column, we might draw kind of vertical lines. Okay, note these are not ones. They're just indicating that we're taking up the whole column of that matrix. Okay, so C1 is the vector representing the entire column. Or we could do the same thing for rows. Okay, so I might have a row vector. Row vectors being the rows of the matrix. And sometimes we might leave it like this, but I think it's a little clear if we have horizontal lines here indicating that these vectors are filling the entire row. It's not just a single entry. The main diagonal of the matrix. Matrix A are all entries Aij of A such that I is equal to J. Okay. In other words, it's all the entries where the row and the column are the same number. Okay. Let me show you what that looks like. Okay. So here I have a 3x4 matrix, 3 rows, 4 columns. So I want all the entries along the main diagonal. The entries along the main diagonal are going to be all the entries where I is equal to J, where the row number and the column number are the same. So I want the entry in row 1, column 1. So that's this one. Okay. So this one's along the main diagonal, A sub 1, 1. Also, if I'm in row 2, I want the entry also in column 2. That entry would be along the main diagonal, so that'd be A sub 2, 2. And so on. Third row, third column, A sub 3, 3. Notice in each case the subscript, the row number, and the column number are the same. 1, 1, 2, 2, 3, 3. And so if I take those together, that's my main diagonal. Starting from the top left corner and then going diagonally down. Okay? And just one more term. A square matrix. Square matrices turn out to be pretty useful, pretty important. A square matrix is a matrix with the same number of rows and columns. So if you have 2 rows and you're a square matrix, you must have 2 columns also. I believe all these examples, none of them appear to be square. This one, definitely not square. I have 3 rows, I have 4 columns, they're not the same, so that's not a square matrix. Okay? Here's a square matrix. I have 2 rows, I have 2 columns, so it's a square matrix. Here is another square matrix. This one has 3 rows and 3 columns. Okay?